Let's go ahead and start with the shear force and talk about how we actually develop a function v of x. So while we already developed a feel for the different types of functions throughout our last lectures, I now want to really develop these functions in terms of x. And to do that, I will start with a very simple case where I actually have a beam that has a support reaction on the left side, and on the right side I actually will cut the beam, but here this is called RAY, let's say, and on the right side I have cut the beam, and now I want to introduce a force case on this. And of course, let's not go with the super easy case with concentrated force. Let's just start with a evenly distributed force, so that we can call that W or W1. And when we do that, we of course always bring in our internal forces from our study card. So we have first the moment, we have the shear force, and we have the normal force, which of course in this case you can already tell is equal to 0. But these are my different internal forces, which now I have to solve at that cut. And you have seen this before, and usually you have seen it so that the distance really here was a finite increment. So let's say from here to here we used to have, let's say, 3 meters, and then we were usually able to calculate it if we had numerical values for our support reaction and our distributed force. But today I want to actually take it to a different level, not a finite level, but an infinite level. And so I want to, of course, describe everything in terms of x along the x-axis, so that I can describe the shear force and later on the moment in terms of x. So what I really want to do here is I want to describe the shear force as a function of x. So let me actually erase all the other parts here that I'm not worried about in this section. I will later worry about the moment. For now, I just want to focus on the shear force. And the way I can calculate the shear force as a function of x is actually very simple compared to what we know already, because we have done it many times before just with a finite number here. And so all I have to do now is to actually replace this 3 with an x. So let me erase those parts as well. So first I want to erase this part here, and then I'm not going to think of x as 3 meters. I actually think of x as a variable, and this might be in meters or it might be in any length unit really, and then it grows in this direction. And so now I can really use the knowledge from before to calculate my shear force, because nothing has changed. It's still that the sum of the forces in the y direction is equal to 0, and 0 is really equal to minus my positive defined shear force of x. That did not change. It's just called shear force of x now, plus RAY. So let's actually color code this. Plus RAY. And then minus W1. And now guess what it's multiplied with? Exactly, it's multiplied by x. So x. And x in this case is in meters. And W1 is, of course, in, let's say, Newton per meter. And RAY is, let's say, in Newton. And of course, the shear force then also comes out in Newton. And if I rearrange this now, I actually have my shear force function already developed. So I can say that my V of x is really nothing else than plus RAY minus W1 times x. And the whole thing needs to be multiplied by Newton in this case, or force. It doesn't really matter what it is, as long as it follows the units that I used in my example here. And so we now developed the shear force function for an evenly distributed load case, of course, this is at the left side of the beam, so that is within the first domain, if you will, but this is my answer. So please understand that, of course, if something now changes here, if I have a different load case on the right, I would have a different domain to deal with. So please understand that we have to think of this as a function per domain, right? Function per domain. And I think that now is everything we need for an evenly distributed load case. Let's now think about the shear force for a non-evenly distributed load case. And to do that, I will redraw a very similar beam. And just for an example, I start at the support reaction again, but I could really start anywhere in my system. So for this beam here, I have a support reaction here once again, RAY. And the non-evenly distributed case that I'm choosing here is a triangular load case. And please understand that usually it continues somewhere here. So I'm actually drawing a little bit more than what my cut is, because I need to explain to you in a second how I actually get my values for the slope. But first, let's bring in our unknown, which is the shear force that on the right cut would go down. And we want to have V of X just like before. And I want to also solve everything in terms of X. So I'm just moving along X. So to do that now, please let's take a look at the shear force one more time. Let's understand that the shear force here is W times X, or I should probably point to this here. Remember what we always said in this class, W times X is nothing else than the base, right? So this is the length and this is the height. So effectively we're calculating base times height, which is the area content. So we have to do the same thing with the triangle now. But we have one problem compared to this scenario here. The triangle is calculated by, remember, let's write down that formula first. So the area of a triangle is really equal to base times height divided by 2. And so we have the problem now that not just the base is a function of X. Here, remember, the base was a function of X, which is of course the case here as well, but our height is also a function of X. And you can see that right here. If I move further to the right, my triangle grows and grows. So the height really increases as X increases. So in other words, I need to somehow express the height in terms of X. So I say that again, for the rectangular case above, we really had the B as a function of X. But now we also have H as a function of X. And so we need to calculate that. And to do that, I think it's easier if I give you a number example. So let's just pretend that the entire triangle here had a length of, I don't know, let's say 6 meters. And we had a value of W that up here at 6 meters actually was, let's say, 12 kilonewton per meter at that particular location. And so what that means is that our beam actually extends past the cut and of course may even extend past the triangle, but our triangular load case may be over at this location, where then here we have the 6 meters. And so that means we can now calculate the slope of this line, and the slope is really nothing else than the rise over the run, right? So we have, in this case, a slope of 2. So let's actually document this. Slope is equal to 12 over 6 in our case, which is 2. But now please be very careful with that, because this unit is technically lying to you. The reason engineers represent this with kilonewton per meter is to indicate that we have a distributed force. But in reality, this 12 kilonewton per meter is only acting at this location at 6 meters. So really, this should be kind of 12 kilonewton. But remember what our goal is here. We want to express the height in terms of x. And so at location x, we need to find the height. Let's actually introduce that into our drawing here, that I want to find the height at, let's say, x. So let's say this here is the height at x. And the best way to describe this so that the units really come out is I can say that the height as of x, which should also be in units of kilonewton per meter, corresponds to x in meters in a similar way as the 12 kilonewton per meter corresponds to the distance that is described by the 6 meters here. And so now I have related this triangle to this triangle, and I can go ahead and actually rearrange for my height. So my height as a function of x is really equal to x meters multiplied by 12 kilonewton per meter, and the whole thing divided by the 6 meters. And so you see that we end up with a slope of 2, 12 divided by 6. Of course, we knew that already. But what we need to understand is that this meter really cancels out this meter, if you will. And so we end up with a unit of kilonewton per meter, which once again is a little bit tricky because we only have that at a specific height. So in this case here at this height, we have this unit. And of course, it's actually a kilonewton here. But again, we use this unit to describe that it's a distributed force. But what we understand now is that h is really equal to 2x. And so h is now a function of x. And again, that's in kilonewton per meter, which now I can use in my shear force function. So let's go ahead and develop the shear force function. So remember that we start as always with the sum of the forces in y is equal to 0. And I use upwards positive. 0 is equal to, I start with my unknown, minus positive v of x. That did not change. The other thing that didn't change is that I have to include ray, that's going upwards, so that's plus ray. And now we need to include the triangle for this length here. So I have the base as a function of x and the height as a function of x. So base times height divided by 2 is really x in meters multiplied by the height, where the height was equal to 2x, and that unit was kilonewton per meter. But now keep in mind that it's a triangle, so I have to multiply the entire thing by 1/2, and because it's pointing downwards, I have to subtract it. And what you see now is that we have an x and an x here, and that is the explanation why the shear force function for a distributed force that is triangularly distributed must be quadratic. We have x and x that actually comes out as x squared. And I have shown this to you before, and you have probably used it before, but now you know precisely where it's coming from. It's not random, and it's not something you need to believe. It's something that you can actually prove by writing out the shear force function in terms of x. And you will find that you have an x multiplied by an x. And if we now collect our terms, we will find out that v of x, the final function, is really equal to plus ray, and then minus, in this case, it's only x squared, but this is a particular case because the slope happens to be 2 here, so it cancels out the 2 over here. But of course, this could be any factor really, and so sometimes you end up with a factor here as well. But you see now that I have a function that is in terms of x squared, and I, of course, report that in force units. So the shear force, of course, always must come out in force units, and you can prove that that is the case because now your units here perfectly match. This, of course, would be in kilonewton, and this here comes out in kilonewton as well. And that is really our shear force function, which I will now double underline so that we can conclude that this is our function and our result for triangular load case. So that's what we see here, and I believe this concludes our shear force function. You can of course take it now to a higher level, and I invite you to do this for, let's say, a parabolic load case. So you could, instead of a sloped line here, actually have x squared as a load case, and then you can use the same technique to develop your shear force function v as a function of x. And what you then would find, of course, is that you end up with an x cube here, and so on and so forth. But I think you get the idea and you see where that's coming from now. So let's now move on to the bending moment.